What's up, YouTube? I'm Tristan Allison. I'm an engineering major with a focus in civil.
I'm Russell Green. I'm an engineering major, and I'm also focusing in civil.
And my name is Peyton Lawyer. I'm a mechanical engineering major, and we're from Bryan College in Dayton, Tennessee. For our project, we chose problem B, which is spinning a wheel. The wheel has a bird on top of it that moves in a way that causes what looks to be perpetual motion. We want to figure out why exactly this happens.
So the main question we had is, can a movable mass machine cause a wheel to spin continuously such that an external drive force is not needed?
Our team's attempt at this scenario led us to a model rooted in Newtonian mechanics. We utilized an uncoupled system of ODEs, one equation to account for the change in angle with respect to time, and the second to define the radius of the bird's center of mass as a function of the angle. The design of this system will be based on examination of the torque equation. The torque in this system will be caused by the force of gravity acting on the mass, which is the bird. The equation for angular torque is moment of inertia times angular acceleration equals torque, where moment of inertia is equal to mass times the radius squared. Based on these relations, increasing radius will increase torque, and decreasing radius will decrease torque. There are some assumptions in our model that we need to address. First, the cockatoo behaves as a point mass throughout the system. Also, dissipated forces drive angular velocity to approximately 0 in 2 pi or full rotation increments. When this happens, the change in rotational energy after each rotation is approximately 0. There are also assumptions we make about the physical properties of the system. First, the mass of the cockatoo is assumed to be 0.352 kilograms, which is the average mass of an adult cockatoo. Second, the radius of the wheel, which is modeled by L, is assumed to be 0.33 meters, which is a pretty normal length for the radius of a bicycle wheel. The distance from the the distance from the cockatoo's feet to its center of gravity is assumed to be 0.165 meters, which is half the height of the average adult cockatoo.
Now for the actual building of the model. Our model is based on the concept of systems of ODEs, particularly uncoupled systems of ODEs. This method allows for separation of the angular velocity and the radial variation, which causes the driving force. A quick definition of uncoupled systems of ODEs is a system of two ODEs is uncoupled if one of the differential equations does not involve one of the dependent variables. To begin our modeling, we took data analysis using slow motion software. So we watched the video and took pi/4 angle increments, and we recorded the time that was associated with those. Using that data we collected, we plugged it into Wolfram Mathematica and used a nonlinear fit command to find our theta equation. This nonlinear fit produced an equation with the R value, which is the deviation from the actual, to be equal to 0.99345, which is very close to the actual model. From there, we just took standard time derivatives to find angular velocity and the angular acceleration. From there, our radial equation needed to be built, and that was based on maximizing the radius at pi/2 and minimizing it at 3 pi/2, which created a torque when the bird is on its way down to exceed the torque caused by gravity working on the way up. This is our basic radial equation, which is the bird's length to the center of mass plus the radius of the wheel. And then this 0.5b sine theta is the variation of the bird. When he extends, it's a little bit bigger, and when he's going back up, he shrinks down and makes himself a little bit smaller, which is modeled by that sine function. From there, we can plug the theta equation in that we found previously, and we find radius position, radius velocity, and the radial acceleration for our model.
Now the graphical analysis of our model. And the accuracy of our model can be best observed by the graph for the angular equations in relation to the radial equations. And these are the position graphs. In the top left graph is our data that we recorded from the video, and the line is our model that we found. And you can see it closely fits the data. In the bottom right is just the change in the radius of the bird's mass over time. And this is, the top left is our angular velocity, which shows the bird speeding up as it goes down the wheel, and it slows down as it goes up the wheel. And the maximum velocity under our conditions occur at the bottom of the rotation at theta equals pi. And we found that the maximum velocity is 5.6 radians per second. And then the bottom right, the graph is at which is the rate at which the radius of the bird's mass increases as it goes around the wheel. And this top left graph is the angular acceleration versus time. We'll use angular acceleration for our torque equation later. And the bottom left is the radial acceleration, or the acceleration of the bird's change in its distance from the center of the wheel.
There are some limitations in our model. First, if the velocity at 2 pi is not approximately 0, the angular velocity will continue to increase with each rotation. Time increments will change and the model will break down and fail. Also, the bird must change its radial position along a continuous path throughout the model. If the change in position of the bird is not continuous, the equations will no longer be differentiable and the model will fail. There are also some errors that could arise in the modeling. In our situation, the process was idealized. In a physical situation, varying air resistance and friction will introduce inconsistencies in the model that could possibly lead to error.
And finally, we can draw a few conclusions from our radial and angular equations from above. First is the moment of inertia equation, which, as you can see, is very similar to our radial equation, which makes sense because it's just the radius squared times a constant mass. And then for the torque equation, which is the driving equation for our system, the torque is caused by gravity, and as you can see from the graph, the left side of the graph from 0 to approximately 1.1 is positive with a maximum at about 2.1 newtons per meter. And the right side of the graph is negative with a maximum at only about 1.9 newtons per meter. This makes sense for our system because the torque needs to drive the wheel back to its starting position, so it has to overcome that gravity. So the positive should be a little bit greater than the negative. In conclusion, we believe that this scenario can best be modeled using a system of ODEs which describe a changing radius in a manner which the radius is maximized from 0 to pi and minimized from pi to 2 pi, which results in a scenario where the torque from 0 to pi is greater than the torque from pi to 2 pi, and the rotational system can overcome dissipative forces. This proves that the system does not require perpetual motion, but can be feasibly created using a machine that radially moves a mass at a rate dependent on the angle.